So, I want to start talking about rational functions. So what a rational function is it's just a polynomial divided by a polynomial. There'll be a few more more set on that definition, but that's the idea of what rational functions are. In order to motivate that we've seen those, let's just answer some yes/no questions. Are the following polynomials? Is 5 a polynomial? Yes or no? Folks for yes? Anyone for no? Those of you who said yes, what is the degree? It is a polynomial. It's a degree 0 polynomial. So any constant is a polynomial. Sometimes it's just silly to think of them as polynomials. That's a degree 0 polynomial. 1 divided by x, is that a polynomial? Folks for yes? Folks for no? Perfect. Yeah, you're not allowed to divide by x. You're allowed to divide by a constant in a polynomial, not by x. Is that next thing, which is a sum of some coefficients next to powers of x, a polynomial? Yes? Yeah, absolutely. That's exactly what a polynomial is supposed to mean. A polynomial is a bunch of added up powers of x with numbers next to them. The next thing, x plus 1 over x minus 1, is that a polynomial? Folks for yes? Folks for no? Yeah, you aren't allowed to see x's in denominators. Polynomials can only have constants as denominators. This is not a polynomial. That third thing, that's 3 degree 1 polynomials all multiplied together, is that a polynomial? Folks for yes? Yeah, what degree is it? Perfect. Imagine foiling it out, the biggest degree you would see is 3. But these functions, like they're not polynomials, but surely if we know how to deal with polynomials, we know how to do stuff with them. If I told you to set one of those equal to 5 and solve, you could do it. That's what we'll start building today. We will start studying things called irrational functions. A rational function is a ratio of polynomials. That's why it's called a rational function. Same reason a rational number is called a rational number, because it's a ratio of whole numbers. So any function of the form p of x divided by q of x with p and q polynomials, that is called a rational function. So let's just do a quick check. Are these rational functions? Is this function that is a polynomial divided by a polynomial a rational function by that definition? Is it a polynomial divided by a polynomial? Folks say yes? Yeah, of course it is. You see the polynomial and the other polynomial in the division sign. The next one, x cubed plus x plus 1, is that, yeah?
So for the fourth one on the example, you said x can be in the denominator. How is that different from the first one of the rational function?
So this is not a polynomial. It is a rational function. So there are 2 classes of things. So it's not a polynomial, but it is a rational function. So these are 2, it's a larger class of objects. So many things that are not polynomials will be rational functions. Just how like 2 over 3 is not a whole number, it is a rational number though. So same sort of idea here. So this is a bigger family of functions. So the next example, x cubed plus x plus 1, is that a rational function? Is it a polynomial divided by a polynomial? Folks for yes? Folks for no? It is yes, a rational function. Why?
Because you could rewrite it as like that function over 1.
Perfect.
1 is a polynomial.
Excellent. This was intended to be a trick question that absolutely everyone would get wrong. Because it intuitively shouldn't be. You wouldn't want to think of this as a rational function. You want to think of it as a polynomial. Every polynomial is a rational function, though. Groovy. Next one, is this a rational function? Yeah, of course, for the same reason. 1 is a polynomial, x cubed plus 1 is a polynomial. Oh, sorry, I should put the yes and the yes here. Thanks. X plus the inverse of x, is that a rational function? And I'll give people a moment to meditate on it. Could you rewrite that as a polynomial divided by a polynomial? Folks for yes? Anyone for no? Cool. So let's try to write that as a ratio function. So those of you who did say yes, what would you want to do if you wanted to write that as a single fraction? Yeah.
Wouldn't that be like 1 over x if it's the negative power exponent?
Yeah. So that's the same as x plus 1 over x. So now I see a polynomial plus a fraction. How would you want to write that as a single fraction? Yeah.
You can make that into more of like a improper fraction where you just multiply the two x's together, then you add that plus 1, then you have the single x on the bottom.
Yeah, you could get a common denominator, x squared over x plus 1 over x. I'll ask that you not shop for motorcycles during class. Sorry, I can absolutely see your screen. Just try to stay reasonably on topic. Sorry for the call out. So now it is literally a fraction where you see a polynomial divided by a polynomial. So yeah, that's another rational function. And finally, that last complicated looking thing. Does that look like you could do some stuff to write that as a single fraction? Yeah. I don't think I want to do it, but one could. So that is also a rational function. I don't know why this time I'm saying that that is a rational function as opposed to just yes, which I wrote for all the other ones. Cool. People feel pretty okay just about what a rational function is? Nice. Let's talk about how to walk with them. Yeah.
This is just a general question. So like for that last one, will we have to try to convert it into a fraction for like a quiz or exam or even a homework assignment?
Depends what you wanted to do with it.
Okay.
Suppose I gave you that and asked you to find any X-Intercepts.
Okay.
Then it would probably be reasonable to, as step 1, try to write that as a single fraction.
Okay.
It wouldn't be a necessary step, but I think it would be the right place to begin. So it depends on what you want.
Okay.
And it wouldn't be that hard to do, right? Multiply and divide this by x plus 3 times x plus 1. Multiply and divide this by x minus 2.
Okay.
People feel okay? Maybe I should ask, does anyone feel like if they were asked to write that as a single fraction, would be unable to do so? Okay, perfect, yeah. Notice I didn't say correctly. Like, there are lots of steps in the process where you can make a mistake. Nice. Groovy. So, one of the things that you often do with rational numbers is you cancel common factors. Like, if you saw, I don't know, 4 over 10, how would you want to rewrite that? Yeah.
Just 2 over 5.
2 over 5, right? You would cancel any common factors. We'll do the same thing with rational functions. If you want to see a rational function like that, does the top and bottom have any common factors? Yeah. You can cancel them. Because of course you can. That's how division works. And so a lot of times, I'll assume at the beginning of anything I do that the rational function that I'm working with is in a reduced form. So, graphs of rational functions. Much of the goal of today is going to be what does a graph of a rational function look like? How do you find things like its intercepts and its asymptotes? And what does the word asymptote mean? So, let's talk about this to begin with. So here is the graph of a rational function. Here's the graph of y equals 1 over x. If you want to see this function, and we're just asked, is that graph the graph of a polynomial? You would say no, right? It's not the graph of a polynomial. What's the behavior that this graph has that polynomials don't? Yeah.
Can I say it had an asymptote?
Yeah, great. Yeah, let's put this into words. Do you want to talk about the vertical or the horizontal? Cool. So you see a spot here where something weird happens. So close to x equals 0, the y values are getting, I'll use some maybe slightly imprecise language, infinitely big. The y values are getting very, very big. Does that happen with polynomials? If I look at a polynomial and try to plug in numbers close to any number, the result won't be arbitrarily big. If I try to plug x equals 0 into a polynomial, I'll get some finite number. Polynomials don't do that. And let's also see another difference. Either by looking at the graph or by looking at the definition of the function. What's the domain of that function? Yeah.
All real numbers but 0.
All real numbers but 0. You can't plug 0 into this function. That's a property that polynomials never have. Polynomials are defined everywhere. If I give you any polynomial, you can plug any number into it. So there's another difference. So let's focus on this. You said vertical asymptote, and I decided not to write vertical asymptote. Instead, I said the y values get big. Well, let's talk about vertical asymptotes. And let's build up that language just a touch. So here's a behavior that rational functions will have. So let's suppose you have a rational function of the form p over q, which is in reduced terms. And I know I've said reduced terms before, but I didn't actually define it. Let's talk about what reduced form should mean. And let's talk about it by just saying what it's not, and even for like a fraction. Is that fraction in reduced form? Yeah, why not?
Yeah. Can't you divide that by 7?
Yeah, both the numerator and denominator have a 7 in them. Is that in reduced form? Yeah, so that tells you what reduced form means. The numerator and denominator shouldn't have any factors in common. So going back over here, the graph of a rational function, p over q, in reduced form terms, meaning that p and q have no common factors. So they can't have any factors in common. Didn't need to use that much space. Such a rational function will have no jumps, no breaks in its graph, except at the zeros of the denominator, where the y values on the graph will shoot up to plus or minus infinity. And that makes sense, I think. Right? If you're dividing by something that's really close to 0, the end result should be something that's really big. That's all that that's saying. If you divide by something that's close to 0, the end result is big. With that in mind, Let's define this. An asymptote for a curve is a line which is chosen such that the distance between the graph and the line gets really big as long as you look at a really big y value or a really big x value. So let's go back to the graph of 1 over x. There it is. Are there any lines that graph seems to get close to when x is big or when y is big? Yeah.
0?
0. X equals 0 or y equals 0? Yeah.
Y equals 0?
Y equals 0 will do. It's a trick question though, like the correct answer would have been either. So y equals 0 is an asymptote. There's the line y equals 0. There's the graph of the function. Do points on the graph of that function seem to be getting very close to that line? Yeah. So this has an asymptote at y equals 0. Does it have another asymptote? Is there another line that this gets close to? X equals 0. If I take really small y values, that graph gets very close to that line. So this graph has a vertical asymptote at the one of those two lines that's vertical. It has a horizontal asymptote at the one of those two lines that's horizontal. Nice. People feel pretty good? Cool. So here's what I'm going to have us do. There's a particular reason that I'm going through this example, because there's a particular behavior I want to illustrate. But here's an exercise to do. Let's sketch the graph of a function which has horizontal asymptote at y equals 2. So I'll draw a line at y equals 2. I'm incapable of drawing an actual straight line to save my life, but that's supposed to be a straight line at y equals 2. And also has a vertical asymptote at x equal to 3. That seems about x equals 3-ish. And another one at x equals negative 2. Draw a graph which has those asymptotes. And there are many, many examples. I'll draw an example in a moment, but I'll give people a chance to draw whatever they want to draw from. So I'll start drawing something. So I need to get close to this y value. So I should start pretty close to that horizontal asymptote. And maybe it goes up and down some. That's fine. I need to get to that vertical asymptote. So let's get there. And maybe from there I jump up to plus infinity. That's allowed. Cool. There is an example. Does anyone have any objections or complaints about this example? Yeah. It crosses the line y equals 3. And that's exactly the objection that I anticipate. And I want to emphasize, rational functions are allowed to cross horizontal asymptotes. That's very much allowed. And maybe we'll pull up a computer-generated graph just so maybe you believe that I'm not talking nonsense. A graph of a function is permitted to cross its horizontal asymptotes. They don't have to. But there's no law preventing it. A function can cross its horizontal asymptotes. A function can never cross its Vortical asymptotes, but that's just because of the Vortical line test. Right? Imagine that this function crossed those Vortical asymptotes, but still had those as Vortical asymptotes. So if I included this like little green piece on that graph, have I violated the Vortical line test? Yeah, so a function will never cross its Vortical asymptotes, but that's just for reasons of, Vortical line test. Cool. How do people with me? Do people want to see like an actual computer-generated graph that crosses its horizontal asymptotes? Their demand? Let's do it. So here is an example. So I'll see if any of these already do the trick. No. So I'll start with something that you might object to because it's not a polynomial. There's the sinusoidal function. In fact, let's do that. Delete the rest. So, in looking at that function, does it appear to have, let's also go to y equals 1. Does that black graph seem to get really close to that dashed red line? So it has that as a horizontal asymptote. But by looking at this, does it look like the black graph touches that red line a few times? Yeah, that's allowed. Even for rational functions. I know this isn't one. It's allowed. People feel okay? Nice. There will be less contrived examples in the graphing exercise at the end of this particular chapter section in the notes. So, let's talk about finding Vortical asymptotes and finding X-intercepts. So here's one observation. Suppose you have something in reduced form. Let's try to find its X-intercepts. And let's just remember how you find X-intercepts. How do you find the X-intercepts of a function?
So y equals 0 for your function.
Yeah, you set the y value equal to 0. And the y value is the function value. So if you want to find the X-intercepts, you would set p of x over q of x equals 0. And what would you want, how would you want to solve that? What would you want to do to this equality? You can't solve it all the way. You don't know what p or q are. But what would you want to do to simplify this equation? Well, I see division on the one side, and that's annoying. So I can get rid of the division by multiplying both sides by q of x. Let's do that. Let's multiply both sides by q of x, giving me p of x equals 0 times q of x. And what is 0 times anything?
0.
Always 0. Oh, cool. So does q actually matter in this question? No. So here's the takeaway. If you want to find the x-intercepts of a rational function, p of x over q of x, just set the numerator equal to 0. That makes sense? Similarly, if you want to find the Vortical asymptotes, just figure out when you divide by 0. If you want to find the Vortical asymptotes of p of x over q of x, just set the denominator equal to 0. And let's see this in action by using it to find some things. So here are 3 irrational functions. Let's try to find the x-intercept. And let's also try to find the Vortical asymptote. I think that'll be enough space for each. So according to the instructions above, if you want to find the x-intercepts of this, what do you need to set equal to 0?
Numerator.
The numerator. So you need to set color code for emphasis, that equal to 0. And what is the solution to that equation?
1.
I think -1?
Let's do that.
Cool. You find the vertical asymptote by setting the denominator equal to 0. So to find the vertical asymptote, I'll set that equal to 0. When is that equal to 0? Nice. Cool. So it's straightforward enough to find the X-intercepts and vertical asymptotes of a rational function. Well, I say straightforward enough, but sometimes it's like really hard to set a polynomial equal to 0 and solve. As long as it's degree 2, it's definitely easy. If it's degree bigger than that, then maybe it's kind of dicey. But these examples are all degree at most 2, so let's try to do them. So here is a rational function. Go ahead and do some work and find for me its X-intercepts and its vertical asymptotes. I think I'm just going to pause for a moment. You will find these things and we'll come together. Good. So, that top function, where are the X-intercepts? I hear one. Is there another one? By that? Where are the vertical asymptotes? That answer isn't wrong, but I'm going to tell you why I'm not happy with that as an answer. What you did is totally correct. You set the denominator equal to 0 and you solved correctly. That's beautiful. If you wanted to actually graph that, unless you have access to 4 dimensions, it's really hard to graph complex functions with complex inputs. So what would be equally valid to say is there are no, and maybe if you want to emphasize, real vertical asymptotes. All right, so at close to x equals I, the values on the graph do get arbitrarily big. But instead of getting close to like a line, they're really getting close to like a complex plane walk of numbers. Because you have too many dimensions to walk in. Does that make sense? Excellent. Next problem. So tell me, where are this thing's X-intercepts and vertical asymptotes? Cool. X-intercepts? Are there any real X-intercepts? No. Good. You could have just said that without me prompting the direct question. Where are the vertical asymptotes? X equals 1, no real X-intercepts. It would also be technically correct to say x equals like plus or minus the square root of 3 times I guess. Yeah. But when you're graphing, you don't do anything complex anyway. everything's real when you're graphing. Cool. So, the next goal is talking about horizontal asymptotes. And strategy one for finding horizontal asymptotes that I will espouse is just do some long division. So in order to find the horizontal asymptotes of this rational function, let's try to just do some division. So let's see, this says I want to know how many times does x minus 1 go into x plus 1. So to write that as polynomial long division, I guess it would be like this. Actually, C. So let's just run through the algorithm. When you want to divide a polynomial by a polynomial, you look at leading terms and then revise what the leading term is. What do you need to multiply x by to get x? Yeah, right? X times 1 is x. So then you take the 1, you multiply it by x minus 1, and you subtract. That will be minus x minus 1 times negative 1. So that's minus negative 1, so plus 1. This 2 is now lower degree than x minus 1, so there's a remainder term. So this division results in 1 with a remainder of 2. And so, what does that say? That says that this fraction is actually equal to 1 plus 2 divided by x minus 1. So if you're like me, then a lot of times, especially when you're dividing two things that are about the same size by each other, I find it very hard to remember which goes here and which goes there. I think that I did it right. Maybe I'll ask for confirmation. Did I actually do the division correctly? Does anyone feel confident that I did division correctly? Does anyone feel unconfident that division is correct? Cool. So let's do something to double check. What's something you can always do to double check that division is right? You can multiply, right? So let's do a quick thing to double check this. Sorry, this is slightly cheating. I taught this same section an hour ago, so like I have memory of what the answer was. But 1 hour ago exactly, I was feeling very nervous. And so, let's do the double check. If this is correct, then 1 plus 2 over x minus 1. If I take that and multiply it by x minus 1, it had better be equal to the thing in the numerator. Right, that's what division should mean. So let's just distribute this out, see if it works out correctly. X minus 1 times 1 is x minus 1, plus 2 over x minus 1 times x minus 1. Those two things now cancel. Divide by a thing, then multiply by a thing. Those should cancel. Is that the same as x plus 1? Okay, good. Then I'm not feeling nervous anymore. This division is actually correct. So how many people, whenever they do polynomial division, feel nervous that they probably made a mistake? Here's the thing you can always do to double check. So, here's the payoff. Now that we've done that, if I graph this function, then I've graphed that function. So let's use that. So what do I have from the previous step? X plus 1 over x minus 1 is equal to 1 plus, let's not write it that way. I'll write it in a slightly sillier way. 2 times 1 over x minus 1 plus 1. So that's a silly way to write that. Like, that's not the way that you would naturally want to write it. But now, does this just look like a stretched and shifted copy of 1 over x? Yeah, and I know what the graph of 1 over x looks like. 1 over x we've drawn it a few times. So let's try to do this by starting with 1 over x. So let's start with y equals 1 over x. There's its graph. And there's like an order you're supposed to deal with these ingredients. What's the first one you're supposed to do? Yeah.
Well, typically, the first order will be like parentheses, but we don't need to parentheses, but, well, if we're talking about PEMDAS or, I don't know, what's the order of bars?
Kind of. So when you're thinking about how to graph, you kind of want to think in roughly the opposite way. Like if you're graphing, first you want to think about what this 2 does to the graph. So what will that 2 do to the graph? It'll like stretch it vertically. That's right. So y equals 2 over x. That will result in all of the y values getting doubled. And maybe we'll just check one thing really quick. This thing has a horizontal asymptote of y equals 0. If I take y equals 0 and double all the y values, I now have a line of what y value? Still 0? Right, you double 0, you get 0. If I take this vertical asymptote of x equals 0 and double all the y values, is it still the line of x equals 0? Yeah, the y values get doubled, so I guess the line gets stretched, but it's still just the same line. So I still have the same asymptotes at x equals 0 and y equals 0. I've drawn them in green parentheses. Next, I need to deal with this -1 and that +1. What will that do to the graph? It'll get shifted, right? It'll shift to the right by how much? And up or down by how much? Up by 1. Good. So let's take this. Let's shift this right 1 and up 1. Maybe I'll start by shifting the asymptotes. So now I see this asymptote at x equals 1 because it shifts to the right. Oh, yeah, sorry. There's another asymptote here at y equals 1 because we shifted up by 1. And now I'll just take that graph along for the ride. Graph will look something like that, I think. People with me right now? Yeah. So, now maybe I'll just copy it down on the actual copy here. So let's see, I drew this as though the x and y intercepts were both negative. Am I actually confident in that based on the walk I did though? How could we check, say, what the x or y intercept is? Could we check what the x or y intercept is? Yeah.
Set the numerator denominator equal to 0.
Yeah. Set the numerator equal to 0 to get the x-intercept. So let's take this numerator, set it equal to 0. What do you get? Cool. So there should, in fact, be an x-intercept there. I guess as long as we're on the topic, how do you find the y-intercept? We haven't talked about that yet today, but we did in the distant past. How do you always find the y-intercept?
Put 0 for, what, just put 0 for the x value?
Just put 0 in for the x value. I guess you then get 1 divided by -1. Oh, hey, yeah, that's negative. Awesome. So there's one way to find it. So, well, now by looking at this, do we just know where the horizontal asymptote is? Have we, in fact, drawn it already? Yeah, where's the horizontal asymptote? At y equals 1. So there's one way to find the horizontal asymptote. Do polynomial long division and see what it tells you. I'll give another way right here in the form of this theorem. So there will be three cases that I'll deal with. So if you have a rational function p over q, first I will ask myself, is the degree of the denominator bigger than the degree of the numerator? If so, then something will happen. So let's just write down an example where the denominator beats the numerator. So there is a rational function, the denominator is bigger than the numerator. The horizontal asymptote recovers what happens when x is big. So let's imagine plugging a really big number in for x. Let's think about what happens when x is big. So when x is really big, that, let's say, 10 to the power 10. So that's a 1 followed by 10 zeros. If you plug that in, then x squared will be a 1 followed by 20 zeros, plus a 2 followed by 10 zeros, plus a 3. Did the 2x over 7 actually make much of a contribution in comparison to that 20-digit number? No, like, it's going to contribute a 10-digit number. That's 1/10 billion, the size of that? 10 million? So when x is really big, the numerator is basically just x squared. By the same rationale, what is the denominator close to when x is really big? Does that 77 make a difference when you plug in 10 to the 10th? No, nothing noticeable. So this is basically x squared divided by x cubed. What does x squared divided by x cubed simplify to? Just 1 over x. Cancel the common 2's. Oh, cool. So now, when x is big, what can you tell me about 1 over x? What's 1 over 10 to the 10 approximately equal to? So it would be like decimal point 9 zeros and then a 1? Is that pretty close to 0? Yeah. There's the logic. So whenever q is bigger than p, this same process will work. The horizontal asymptote will be close to y equals 0. When they're both the same degree, well, let's see something that happens. 2x squared plus 3 over 3x squared plus 2. So, same logic. If you plug in a really, really big number for x, does that plus 3 or that plus 2 actually make any difference? No. So when you plug in a really big number for x, this is basically 2x squared divided by 3x squared when x is big. And what does that simplify to? 2x squared divided by 3x squared simplifies to 2 over 3. 2 over 3. And notice, this 2 came from that 2 came from there. This 3 is the same as that 3. So you could do this for absolutely any polynomial divided by polynomial you wanted. Here's the point. Only the leading terms actually make any difference. So, if you do that, if the degree of q is equal to the degree of p, there will be a horizontal asymptote at the leading coefficient of p divided by the leading coefficient of q. People buy that? Nice. And in the interest of time, maybe I'll jump straight to the conclusion in the last case. If the degree of p is greater than the degree of q, then there will be no horizontal asymptote. There might be what's called an oblique or a slant asymptote. there will be one homework problem on the topic of oblique and slant asymptotes. I will not discuss them in any more detail in class. Instead, I'll encourage you to read that question, read the section in the book that it references, and then ask me some questions about it. So let's use this result to study these rational functions. So let's talk through the first one altogether. What's the degree of the numerator of that rational function? What's the degree of the thing on top? What's the degree of the thing on the bottom? 4. Those are the same. So which of those three cases should I look in? The equal to 1. And this says now that there should be a horizontal asymptote at the leading coefficient of p, that's 1, divided by the leading coefficient of q, that's -2, -1/2. Let's talk through the same, maybe at some speed. Where is the horizontal asymptote of this rational function? 1. Everyone agree? Anyone want to send detail? Where is the horizontal asymptote of this? What's the degree of the top? Degree of the bottom? So which one wins? The top or bottom? So the bottom wins. Look at so the top bullet point isn't on the page anymore, but it's still on your page. What's the top bullet point in the theorem? Yeah, so 0. That's why the thing is there. And the final one. Where are its horizontal asymptotes? No. Maybe I'll put this vague statement here. What's the degree of the top of that fraction? 5. The degree of the bottom is 3. So 5 minus 3 is 2. So asymptotically, I will assert that this will behave like a degree 2 polynomial. Asymptotically. Neat. So, let's see, with 1 minute remaining, I think we can do just a little bit more. So let's go to something that is bordering on an actual real application. I have 2 minutes, not just 1 minute. So let's just read this example. Let's suppose that some model of a B population says that, let's only look at the random population, has population modeled by the function 5t cubed divided by 2, 5. As time goes to infinity, what does the B population get close to? So this is asking when the input is really big, what is the output close to? That's exactly what a horizontal asymptote measures. So tell me, by looking at this rational function, where is its horizontal asymptote? It's 5/2, right? So that means when the input is really big, the output is basically 5 divided by 2. So let's just write that down as a sentence. As time gets big, as you wait long enough, the population approaches, gets as close as you want to, 5/2, and maybe now, like, the units were hundreds of nests, so 5/2 times 100 nests. What's over 5/2 times 100? 250. So we can write that in a less silly way. So this population of bees will approach 250 nests in time distance. And now, I think that I am not over time, but I'm at time. So I don't need to apologize for going over it, but I am there. And on Wednesday,